My dear friends, welcome to Rajashekar classes on data structures through C. This is lecture number 58. In this lecture, we will try to understand tree and graph. Tree is a connected graph without any circuits. It must be free from circuits or cycles, or it must be free from closeness. For example, just consider this second slide. This one is tree, as there are no circuits, as there are no cycles. But this cannot be a tree. Why? Because there is a circuit, there is a closeness. Again, this cannot be a tree, as there is a closeness. And this is a tree, there is no closeness. If it has circuit or closeness or cycle, that cannot be a tree, isn't it? Yes, that's what definition says. And another way of defining tree is if in a graph there is only one and only one path between every pair of vertices. There must be only one path in between every pair of vertices. For example, if I consider this one is not tree. Why? Because between A and B, this is one path. There is another path, this like this also, ACB. If there are more than one path between two vertices, that graph cannot be treated as a tree. These are different ways of defining tree. Anyway, now we will try to understand what is graph. Graph means set of ordered pair of vertices and edges. Means it's an ordered pair V comma E, where V is non-empty set of vertices, E is set of edges. There is no restriction on E. E can be empty set or non-empty set. For example, just if I keep a vertex A, we have vertex set as according to definition, V must be a non-empty set. Yes, we have got non-empty set. There is no edges in this particular example, therefore equal to empty set. Still it's a graph. There is a restriction on V, there is no restriction on E. V must be a non-empty set. Example 2, A is a vertex, B is a vertex, A comma B set of vertices, non-empty set of vertices. There is an edge AB is an edge. Still this one is graph. These two examples, they are not only graphs, they are also tree, isn't it? Why? Because there is no cycle in this particular graph. In this particular graph, there is no cycle, isn't it? Therefore, these graphs can become trees, as there is no circuit, as there is no closeness, as there is no multiple paths in between two vertices. Therefore, these are graphs as well as trees. I can say every tree is a graph. Graph need not be a tree. For example, this one is a graph but not tree. Why? Because according to definition, you have set of vertices A, B, C, set of edges A, B, B, C, C, A. It's a graph. Of course, it cannot be a tree. Why? Because there is a closeness here. If you have closeness, it cannot be a tree, isn't it? Now, this example we discussed, isn't it? This one is tree, and second one I can say this one is it is a graph. There is a closeness, but it cannot be a tree, isn't it? This tree is, every tree is a graph. Therefore, this is a graph as well as tree, isn't it? This one is not a tree. Why? Because there is a closeness. If there is a closeness, it cannot be a tree, isn't it? Just a graph. This is only a graph. This one is tree. There is no closeness, there is no cycle, there is no circuit. Therefore, this can be treated as a tree. Of course, every tree is a graph. A graph means there must be ordered pair V comma E, vertices and edges, a vertex set and edge set. Therefore, as every tree is a graph, I can treat it as graph as well as tree. Now, we will try to differentiate between tree and graph. Only one path is allowed. That's what we discussed. In the case of tree, multiple paths are not allowed. More than one path is allowed in the case of graph. It has exactly one root node, root to child like that, but it can have, does not have root node concept, isn't it? No loops are permitted. Closeness is not allowed in the case of tree. Graphs can have loops. Less complex. Yes, tree is less complex. It is a more complex. A tree can be traversed in three ways: pre-order, in-order, post-order. This I already discussed in my previous lectures. Even a graph can be traversed in two standard ways. One is BFS and another one is DFS. BFS means breadth first search. DFS means depth first search. This is a hierarchical type. This is a network type. Hierarchy means root child relation is there. But here there is nothing but root child sort of things. Graph need not be a tree. Every graph need not be a tree, but every tree is a graph. Main use of trees, they are useful in sorting and searching techniques. These are graphs are useful in especially PERT and CPM. You might have learned in a subject known as operation research. This course may not permit me to discuss about PERT and CPM, just understand that graphs can be used in PERT and CPM sort of things. As I told you, parent-child relationship is existed in trees, but there is no parent-child relation in the case of graphs. Applications of trees. What is the use of trees? Trees are useful for representing file system in computer, Linux operating system, Unix operating system. You might have learned file system, root child like that. Chemical formula representation, a hydrocarbon molecule. If you want to represent hydrocarbon molecule, you can make use of trees. Represent if there is an organization, that organization hierarchy can be represented using trees. Text processing methods can make use trees. You might have learned text processing method. There are different Nath-Morris, Pratt algorithm, brute force method, Bayer-Moore method. There are different text processing methods where you can make use trees. There is a concept known as try is a concept. But anyway, this course may not permit me to discuss those things. It is useful in compiler design. There is something like bottom-up parsing, top-down parsing. There one can construct trees in artificial intelligence to represent knowledge bases in artificial intelligence. One can make use these trees. If you want to store large volumes of data, one can make use trees. Even it is useful in telecom network building. Let me take one simple application of graph. If there is an algebraic expression of this form, these algebraic expressions can be represented by trees. A plus B means what? This has got higher priority, isn't it? Therefore, as it is in brackets, therefore A plus B, in between plus I must keep, that must be multiplied with C. Therefore, this is A plus B, this is C. In between star means this is A plus B whole star C. This must be subtracted from D star E. This is D, this is E. Entire thing is D star E. That A plus B star C minus D star. Basically, this is useful for representing an algebraic expression. A plus B star C minus D star E is an algebraic expression. Even graphs can make use in transportation sort of things, in logistics, circuits design, social networking like Facebook data to represent using graphs, social networking, sociology, project management, job scheduling, job sequencing with deadlines, scheduling algorithms, can make use these graphs, timetable scheduling, topological sorting, spanning trees, traveling salesperson problem. You might have learned in your course design and analysis of algorithms, or even an operation research. You might have learned this traveling salesperson problem where one can make use graphs. Thank you very much.